For this server rack video series, we are demonstrating the Vector Q2 power controller in an isolated 3-phase 240-volt breaker panel. This panel includes one server rack fitted with multiple blade servers and storage arrays operating at varying capacities. The server rack is powered on 2 phases, denoted as L2 and L3. The panel also includes sufficient lighting to illuminate the server rack area and is loaded on the first phase, denoted as L1. The Vector Q2 power controller is also installed in the panel. It is installed in parallel with 3 30-amp breaker fuses, one on each phase, inserted into the breaker panel. 3 current transformers are attached on each incoming phase of power. An important note: typical installation of the Vector Q2 power controller does not disrupt power and takes less than a half an hour. The Vector Q2 power controller acquires the input from the current transformers, corrects the electricity with subcycle correction, and displays the data in our user interface.
This is a dashboard that will be used to track results and monitor live electrical data. At the top, we can see the on-off status of the Vector Q2. Currently, it is turned off. Here we can see the 3-phase voltage and current graphs, with the white line as L1, blue line as L2, and orange line as L3. These 3 colors and corresponding phases are the same throughout the entire interface. Here we see the current harmonics bar graph for the first 11 harmonics in algorithmic scale. The yellow bar depicts average of the 3 phases. This is a phasor diagram depicting voltage and current. Voltage is shown by the outermost arrows at 120 degrees apart from each other. The inner arrows depict current. The larger the arrows, the greater the current for that phase. And the further apart they are from the voltage in either direction depicts a leading or lagging power factor. To the right is a table that shows streaming numerical data for each phase with an average. Additionally to the traditional power quality values, you may notice PQ. This is reactive power divided by total power. And PQR, or power quality rating. Components that make up PQR are power factor, total harmonic distortion, ground current, and phase load balance. This can be used as a measure of how effectively and efficiently electricity is being utilized, with 100% being the absolute ideal. Below are charts that track each phase over the span of 300 seconds, with the white line as L1, blue line as L2, and orange line as L3. This chart tracks power in watts. This is percentage of current THD. This chart shows PQ by phase and PQR, or power quality rating, as the green line.
There are many electrical distortions that force current and voltage waveforms from their ideal sinusoidal shape. The 2 most common distortions are harmonics and non-unity power factor. These 2 distortions are the largest contributors to excessive heat and needless wear and tear in the electrical network and to connected loads. The presence of them also impedes the electrical network efficiency, which results in higher repair and maintenance expenses and more money spent on wasted electricity. The source of harmonics in data centers are from loads operating in the electrical network drawing power in a non-linear way. Power supplies in particular introduce harmonics and add excessive heat into the environment. The sources of poor power factor are typically related to the motors running the HVAC and also from various lighting, transformers, or generators. These distortions are always present in data center electrical environments. There is an enormous amount of information from various industry leaders documenting the additional expenses on repair and maintenance of infrastructure and how they increase power consumption. We will include some of these resources in the post beneath this video. Next, we will look at how subcycle correction dynamically eliminates harmonic distortion and maintains power factor at unity. We have turned the power controller on and off for 30-second increments for several minutes. Now we will speed up that footage to demonstrate the difference between when subcycle correction is turned on and off. First, we will focus on harmonics, then we will focus on power factor. If you are unfamiliar with our dashboard, please see the previous video, Part 2, Demonstration Interface. Bottom left portion of the screen individually graphs the current harmonics on each phase in a real-time bar graph. Each column is made up of 4 bars. The bars show the real-time harmonics on each phase, with the first 3 bars color-coordinated to the phases, and the 4th being an average of the 3. The scale is logarithmic and in real time. We have presented the averages on the chart to the left. You can see that the THD was decreased on all 3 phases, with the L1 experiencing the largest decrease from 117% down to 2%. When the power controller is turned on, the harmonics are maintained near ideal and are perfectly balanced across the phases. Less harmonic distortion on the server rack reduces the heat of the connected power supplies and increases the electrical efficiency. Now we will replay the same on and off footage, but focus on power factor. The average power factor on all 3 phases is increased and maintained near unity. The first phase, with just the lighting, experienced the largest increase from 0.41 to 0.99. With the Vector Q2 turned on, this server rack is operating at optimum efficiency. This video demonstration clearly shows the negative effects of uncorrected power in a single server rack. A typical data center has anywhere from dozens to hundreds of server racks, all introducing similar harmonics and power factor as shown in this video. Combined, these distortions increase expenses on power, repair and maintenance of equipment, and contribute significantly to downtime and power disruptions. The Vector Q2 power controller dynamically corrects electricity and eliminates virtually all distortions with the same effectiveness as demonstrated in this video with power factor and harmonics. This includes voltage sags and swells, frequency deviation, ground or neutral currents, noise and resonance, and others. With the 3DFS solution, correction is not limited to server racks. 3DFS provides the same protection and quality of service for HVAC, lighting, UPS devices, and any other connected load. Data center electrical network and all loads operate at peak efficiency every microsecond, year-round with 3DFS. This demonstration is done on a server rack installed in an isolated 3-phase 240-volt panel. Phase A contains a small amount of area lighting and has an average current draw of 0.5 amps. Phase B contains mainly storage and has an average current draw of 4.5 amps. Phase C contains a variety of GPU processing and has the highest average current draw of 18 amps. Also depicted here are the ground and neutral wires. We have exaggerated the load imbalance in order to demonstrate the effectiveness of the automatic phase balancing feature of 3DFS technology. In a typical data center, the imbalance is not as substantial as this, but is always present due to the non-linear nature of server rack power consumption. Please note that the power drawn on each phase from the transformer is identical to the demand on each phase. Now we will discuss the harmful effects and additional costs associated with unbalanced phases in data center environments. Utility companies use historical power consumption data to extrapolate how much power a data center will require at any given moment. To do this, they analyze how much power is drawn on each incoming phase. When the phases are imbalanced, the utility company assumes that the highest peak usage among the phases is the potential usage on all phases. Customers pay for the excess capacity even though it is unused. These charges affect customers differently across energy suppliers, but exist in some form in all of them and can be a substantial percentage of the power bill. Transformers, UPSs, generators, and other electrical network infrastructure underperform, experience wear and tear, and overheat due to the increase in line impedance and reactive power related to unbalanced phases. This results in more frequent repair and replacement of these critical electrical network components and also affects the day-to-day stability of the power network. Neutral wires will carry current when phases are unbalanced, creating safety issues for staff and workers. In addition, neutral line currents increase liability and are notoriously suspected as igniters of fires in homes and businesses. The existing solution for unbalanced loads revolve entirely around manual manipulation of the electrical network and introduce human error at multiple levels. Most data centers attempt to manually balance the server rack loads across the phases by guessing the power consumption on each phase and hoping that it remains steady during operation. Other solutions include load scheduling, which requires cautiously timing loads to turn on or off at specific times in order to avoid large spikes on a particular phase. Also, load shedding, which involves identifying loads that can easily be turned off in order to instantly reduce power demand on a phase. Given the dynamic nature of power consumption in server racks and obvious uptime requirements for data centers, all of these solutions are impractical and fail to achieve ideal load balancing across phases. There are lots of resources from various industry leaders and research institutions describing the negative effects and additional costs related to unbalanced phases. These are a few of them, and we will include the links in the post beneath this video. Now we will show how 3DFS technology is the first commercially available product that automatically balances the loads across the phases, eliminating human error from this process. The power controller analyzes the real-time power demand and immediately optimizes electricity and reports data through our secure user interface. During this process, the load balance across the phases is also monitored and corrected, providing dynamic load balancing at all times. The automatic load balancing feature comes standard with the Vector Q2 unit. The Vector Q2 is installed in parallel in the panel. Before it is turned on, please take note of the current draw before the panel and the current draw on the individual loads. The imbalance is equal throughout the system. When the Vector Q2 is turned on, two things happen. The current being drawn upstream from the panel is immediately drawn with equal balance across all phases, and there is a reduction in the current drawn on each phase at the load level. By automatically balancing the loads across the phases, neutral and ground currents are eliminated, reducing liability and improving safety for equipment and personnel. Peak demand charges and penalties related to unbalanced phases are also eliminated, reducing expenses on monthly power bills. UPSs will have a longer runtime, and generators will evenly deliver greater amounts of peak power, while much less heat will be emitted from the transformers and power equipment. Automatic load balancing is one very important feature that comes with 3DFS technology and assists with zero-waste electrical networks in data centers.